Hey everyone. So we've talked about groups, but now let's talk about rings. So, like we usually do with these sort of introductory videos or these introductory um, discussions about new topics, there are a lot of definitions that you have to go through. So, we're just going to talk through them. So, a ring is a non-empty set R, and we have operations plus or addition and multiplication, and of course you take a pair of elements in R and then send it to a new element in R. And we've also got special elements 0 and 1, such that if you take this set R, considered with the operation addition and the element 0, you get an abelian group. And abelianity is important, so addition will always be abelian in a ring. And furthermore, if we look at R under multiplication with the element 1, and this is a monoid, meaning that multiplication is associative, and we have a multiplicative identity, which is 1. But the thing that makes this different from a group is that you don't have multiplicative inverses, per se. You could potentially have multiplicative inverses in a ring. It could be that every non-zero element has a multiplicative inverse, but you're never going to have an inverse. Well, yeah, for like nice rings, you're not going to have a multiplicative inverse for 0. Yeah. So anyways, and we also have these relations between multiplication and addition. And it's basically distributivity. If you've got A multiplied by B plus C, then you can distribute it like this. And similarly, we can do this if we multiply on the right. And note that we have to state these two separately, because even though we're assuming that multiplication is a monoid, we're not assuming that's commutative. So you can't, multiplying A times B is not the same as multiplying B times A in a ring. Sometimes it is, and we'll talk about that. That's what this is, but in general, that's not the case. So, another point here. Some people will say, let's see here. I'm pretty sure that the convention that we use is that 0 and 1 are different elements. You can prove, and this is something if you're not familiar with rings, you can prove it right now based on all of this stuff, and you should if you haven't seen this proof, that if you have a ring in which 0 equals 1, then the ring only contains one element. And in particular, 0 will be equal to 1. And so what we're going to define here is, I believe we're going to define a ring to be such that 0 and 1 are not the same. So what we would typically refer to as the 0 ring, we're not going to consider it a ring in this course, I don't think. Anyways, so if we look at examples, we have the integers, the rationals, the real numbers, and the complex numbers. All of them are rings where you use addition is just addition of numbers and multiplication is just multiplication of numbers. And let's see, if we're looking at this multiplication, we know that's a monoid. In Z, it's just a monoid, because if you take something like 3, if multiplication were to not be a monoid, that means that every element would have, or at least every non-zero element would have a multiplicative inverse. So in particular, you have the element 3, which is a integer which has no multiplicative inverse, because its multiplicative inverse would be 1/3, but 1/3 isn't an integer. So anyways, it turns out rationals, real numbers, and complex numbers will be fields, meaning that if you choose a number that's not 0, then that number will have a multiplicative inverse, and we'll talk about that more. So anyways, if we have two rings, R1 and R2, then we get a ring R1 direct product with R2. And basically what you do there is, if you take two elements, you add them together by adding the first two elements in R1 and then adding the second two elements in R2. Same for multiplication. It's sort of like the things are just doing their own thing, but you're pairing them together with this direct product. So yeah, if we have a ring, then we also have a ring given by n by n matrices whose elements are, or whose entries are elements in that ring. And that's something, well, that should make sense, because if you add two n by n matrices, you're going to get an n by n matrix, and each of the entries, if you took them both from a ring, then since rings are closed under addition, the entries will be in the ring. And then the other thing is that if you multiply two matrices, if you multiply an n by n matrix by an n by n matrix, you'll get an n by n matrix. And the entries will be given by, there's formulas involving like sums of products of the entries. And of course, these entries are elements in a ring, and rings are closed under addition and multiplication. And so all of the entries in the product of two matrices of elements in here will also be one of a matrix of this type. So this is a ring. Similarly with this, and this notation R adjoin X, this is basically polynomials whose coefficients are in the ring. So if we wanted to write this, this would be like things of the form like a0 plus a1x plus a2x squared plus all the way up to an x to the n, where a0 through an are in R. And then, of course, x is just we sort of think of it as just a symbol in this case. It doesn't really have any meaning. It's just, you can use this, which we associate with x to the 0, and then you've got x to the first, x to the second, and then all the way up through x to the nth power. And those are all just sort of separate things. You think of them as being separate things in this. And of course, for this being polynomials, we consider all things of this form for any n, which could be between 0, which could be any integer that's greater than or equal to 0. So as long as it's finite, you're good. And it should be clear that addition, addition and multiplication is just the typical like addition and multiplication of polynomials that you're used to for working with polynomial functions. It's just that now they have coefficients that are rings. And so for addition, you just find the terms that have the same powers of x to them, and then you just combine the coefficients, and that's how you add them together. And clearly, since the coefficients are in a ring, this new polynomial will be something of this form. And then multiplication is a little trickier. You do that thing that you typically learn in high school, where you take each, if you're multiplying two polynomials together, you take each term in the first polynomial, then multiply it pairwise by each term in the second polynomial. And the formula for that ends up being this. And if you just look at this quickly, it's not super obvious at first that this is how it works. But if you actually look at some examples of some polynomials and like write them out, then you'll see, oh, this is exactly the formula that you get when you multiply two polynomials here. So those are some examples, and now we got a whole bunch of definitions. And of course, as usual, you sort of just have to memorize these. Or you could just start going through like further exercises and stuff, and you'll sort of memorize them by accident if you work enough with these types of things. But anyways, so if the multiplication in a ring is commutative, then we say that the ring itself is commutative. And that sort of makes sense because we know that addition is always commutative because under addition it's an abelian group. And so if we're going to say that a ring is commutative, it makes sense that the only thing that could possibly be the only thing that like is sort of special when it has commutativity is the multiplication. We say that R is a division ring. I usually hear division ring for it. I think skew field, I don't hear skew field as much, but it's another definition. Basically, these refer to the case where if you take all of the elements of R which are non-zero and consider this monoid, this is a group. So basically what that means is that if you take two non-zero elements, multiply them together, you'll get a non-zero element. And every non-zero element will have a non-zero multiplicative inverse. And so in particular, a unit is an element that does have a multiplicative inverse. So in this example, to say that this is a skew field or a division ring, or to say that R is a skew field or a division ring is the same thing as saying that every non-zero element is a unit, because that's exactly what this is saying. For this to be a group, you need to have multiplicative inverses of every single element in R which is non-zero. And so the reason, like, you might see this and think, oh, that's what a field is, if you've seen a field before. Typically you learn about, it's sort of strange because fields are sort of, you have a lot more stuff in them than rings. Like there's more conditions that you need to satisfy in order to have a field. But because they're sort of more natural to think about, you typically learn about them first in like a linear algebra course. So you go from like a really sort of restrictive thing, which is a field, and you talk about fields in linear algebra, but then when you go to abstract algebra, you sort of start at the beginning with groups which have like some conditions on them, and then you go to rings which have more conditions on them, and then if you put more conditions on a ring, you get a field. But anyway, so a field is a commutative division ring. So division rings and skew fields, we didn't say anything about commutativity of this multiplication. So a field is a commutative division ring. We say that a commutative ring is an integral domain, or we might just call it a domain, if whenever you have two elements in the ring, you multiply them together, you get 0, then one of the two has to be 0. And this isn't a super like universal definition to say that, well, I think it is sort of common to think about integral domains as only being commutative rings. But commutative rings tend to be nicer, and typically like we'll say a few things at the beginning that apply to all fields, but then after like a few lectures, you typically start just talking about commutative rings, because that's where a lot of like the neat stuff that you can do in ring theory happens, at least at the like beginner level. So let's see here. So now let's talk about ideals. So if we have a subgroup of the multiplicative group, if we consider R as a group under addition, and we consider a subgroup of this group, so this is something which contains, this is a subset of R which contains 0 and is closed under multiplication. We say that this subgroup is a subring if it contains 1 and if it's closed under multiplication. And it should be pretty clear that a subring is itself a ring. So that turns out to be like, you'd sort of think that's the main thing that you talk about in ring theory. It's like subrings, but it turns out to not be. It's sort of strange because in group theory we have subgroups that we talk about as being like a subset that is also a group, and then we also have kernels and normal subgroups. And normal subgroups are a lot of our important facts have to do with normal subgroups, and this comes from normal subgroups being kernels of group homomorphisms. And it happens in group theory that normal subgroups are subgroups, that kernels of homomorphisms are subgroups. In ring theory, subring is like a subset that is also a ring, but when you look at kernels of homomorphisms, you get ideals. And ideals don't have to be... Let's see here. No, subrings don't have to be ideals. Yeah, it's basically what ends up happening is that subrings play the role of subgroups and ideals play the role of normal subgroups. In some sense, there's some things you have to be careful about there. But anyway, so for ideals, you say we're still considering an additive subgroup. An additive subgroup is a left ideal if RA is an A for every single element in R, or every single R in R and A in A. So we call it left because we're multiplying things on the left. And an important thing to note here is this is like a lot stronger than being a subring. Because first of all, well, sort of, because we didn't say anything about having the element 1 in here. Ideals don't have to have the element 1. In fact, if you just consider 0 by itself, that's an ideal. The element 0, because obviously you take anything in R, multiply it by 0, you get 0. And in fact, that's not a ring, so it can't be a subring. So it is true that ideals don't have to be subrings. But or at least in the truth, yeah. So anyways, so we have, this is true not just for every single thing in A, but we have the stronger thing that this multiplication is, this element is an A for every single R in R. Every single R in the overall ring. Even the things that aren't an A. So that's a pretty powerful condition here. And then a right ideal is the same thing, but you flip it. So the element of the ring goes on the left or right based on whether it's a left ideal or right ideal. And this is for all A and R and R. I didn't want to write them again. And then we just say that A is an ideal if it's a left ideal and a right ideal at the same time. All right, so if A is an ideal, and for some reason I've seen multiple professors use this notation. I haven't seen it as much in textbooks, but it seems to be sort of common to use lowercase, like, if you want to know what the symbol is, I think it sometimes looks like, I don't know how to draw, but it's like, if you were to type it in LaTeX, it'd be math frac and then lowercase a. And I'm not quite sure where this convention came from. A lot of textbooks will use things like capital I for ideal, and they'll use like capital I and capital J, and typically you don't need to use too many more letters than I and J, or if you do, you use like subscripts. But anyways, this gives us a little more flexibility using like this font. But anyway, so if you see something like this, it should look like a letter, and that's what I'm going to refer to it as. So if A is an ideal, then we can form a quotient ring, R mod Q. And this is when we say quotient, we have to be careful because we've got two operations here. And so what we're quotienting with respect to is with respect to addition, which kind of makes sense because that's the only one that's a group, so that's the only one where we really know how to take quotients. So addition just works like this. And for multiplication, here we're actually going to prove that this is well defined, because it's not entirely obvious at first that if you multiply two things together, like something like A plus A times B plus B, that like how do you know that you're going to get something of the form AB plus A? In particular, how do you know this is well defined, i.e. if you choose different representatives from these two cosets, are you still going to get something here? And it turns out the answer is yes, because if you take any element in here, it's going to look like this when you distribute everything out. It's going to be AB plus, then you've got this AB, then you've got this A times A. Here these two A's are the ideals, and then this is A times itself. But because it's an ideal, anything of this form will be in the ideal, anything of this form will be in the ideal, and anything of this form will be in the ideal. And so anything that looks like this will be in here. And similarly, if you have anything in here, then you just let B equal 1, and it should work out. Or, yeah, if you have like A plus alpha here, then if you let, no, not alpha, if you let A plus the ideal here, then A plus the ideal times 1 plus the ideal should give you the ideal. No, that'd be 0. Right? You'd want it to be 0. Right, you'd want it to be 0 because then, no, you would want it to be 1. You'd want it to be 1 because, well, yeah, that makes sense because 1 is the multiplicative identity, and also, so this would be A, this would be 1, this would be the ideal, this would be A times the ideal, which is just the ideal, and this would be the ideal too, and you can prove that this is just going to be the same as the ideal. So yeah, that's how we know that the quotient is well defined. And so yeah, here are a bunch of definitions, and then we'll talk about more definitions and then actually proof stuff.